this case, we're going to select A. Great job. What size copper conductors would you select for a single phase motor with a nameplate rating of 26 amps that will run a drawbridge for only 5 minutes at a time, terminating to 60 degrees C? This is not a normal situation, is it? So that's what you learn to watch out for when sizing motor conductors. Is there anything different going on? And in this case, there is, so we're going to slow down and figure it out. Everyone head to 430.22e. It's on page 302 of the 2017 and on page 313 of the 2020. There are provisions in the code book for when motors will only run for fixed or limited amount of times that you can have a reduced amp draw to size your wire by, or sometimes it's actually an increased amp draw. So it's just really another demand factor. So everybody head there now, pause the video now if you need to. So when we get to 430.22e, we're going to read the black bold heading. It says for other than continuous duty motors. Remember, all of our other motors, we did the 1 point continuous duty. But what if they're not continuous duty? And that's what we're going to cover here. It lets us know that conductors for motors that are used short time, intermittent, periodic, or varying duty shall have an ampacity of not less than the percentages that are listed, okay, in 430.22e. Okay, so these ones we are going to go to 430.22e, and it's a table. It's usually on the next page of your code book. So whether you're in the 2017 or the 2020, it's typically in the next page over. When we get to table 430.22e, let's look at it now, starting with the black bold heading. It says duty cycle service. Pretty sweet. Now using our black bold headings, top to bottom, left to right. Starting on the left-hand side is going to be our classification of service. Okay, so on the left-hand side, we're going to pick whatever scenario our question lists. And if you look down through there, somewhere you're going to find something about a drawbridge, okay, or whatever your question states. Then going across the top in the black bold headings, you're going to see 5-minute, 15-minute, 30 to 6-minute, or continuous duty rated. So with that being said, what you're going to do is start on the left-hand side and find your situation, then come across the top and tee off with your amount of time. So what you will do is, when you get that value, it's just going to be another multiplier. It's just another demand factor. So let's look at the first one. In a 5-minute rated motor for short time duty operating valves. That's the first one you come to on the left-hand side. If you go over to a 5-minute motor, it's 110%. So all you do is take and multiply it by 1.10. It's just another demand factor. All right, so let's look at our question again and answer it. So in this case, we have a 26 amp draw. Remember, we don't use the FLCs on this type of question. You're going to use the nameplate rating. And we're going to have a drawbridge for 5 minutes. So we go to our table, 430.22e, starting on the left-hand side, and let's find something until it says the word drawbridge. Looking down, and if you look right there, in the middle section, it says drawbridges. Now we need to come over and tee off with our respective time. In this case, it's 5 minutes. So we find what type our motor is, then we slide over to our time limit, and we're going to find our multiplier, and we're going to take our amperage and multiply it by that demand factor. In this case, it's 85%. So we take our nameplate rating, multiplied it by 0.85, and that's going to give us 22.1 amps. Now we can head to our ampacity table and size a wire that can hold 22.1 amps, being sure to select from the 60 degree C column. So when we get there, we come on the copper side, 60 degrees C, and let's find a wire that can cover our known load. And in this case, we're going to select C. Great job. What size copper conductors would you select for a 3-phase motor with a nameplate rating of 40 amps running some short time duty operating valves that will only run for 15-minute intervals, terminating to 75 degrees C lugs? One thing I want to note is that if you watched our video back in week 1 that teaches you how to make your own tabs, you should have made a tab for this table, okay? This is one of the tabs that we highly recommend making that are not in the Mike Holt tabs that we sell. So with that being said, you can use your tab for even faster reference to this table. So we see that there's something going on here, and we recognize that it's a duty cycle question. We're going to head to our demand factor table for duty cycles. It's 430.22e. Then starting on the left-hand side, we're going to look for our situation. In this case, it's short time duty operating valves. So when we find it, we come over and we tee off with our time, which is 15 minutes, and we're going to find a demand factor of 120%. Then we take our original 40 amps, multiply it by 1.20. Now we have 48 amps. Let's head to our ampacity table. Let's find a wire that will hold 48 amps in the 75° C of the copper side. And in this case, we're going to select D. Great job. Now we're going to learn about motor short circuit ground fault protection. There are two types of protection for a motor. One of them is called short circuit ground fault protection, and the other one is called overload protection. They are two separate things, and they've named them on purpose so you would know what rules to apply. So let's learn about what they both are, and that way we can rightly divide them. And all I want you to think about, so you don't overcomplicate it, is both of these protections are just breakers and fuses. Okay? And that is was so hard for me to understand at the beginning, is that because you hear these two different types of protection and you can really get lost in the sauce. But all they are breakers and fuses. And I'm going to explain how a basic short circuit ground fault protection and motor overload setup would work now. Okay, so we have both the types of protection. Let's imagine that this is a motor. Next to the motor, there's a disconnect. And then feeding that is a panel. At the original panel is where you're going to put your short circuit ground fault protection. At the disconnect is where you're going to put your motor overload protection. The first protection, the short circuit ground fault protection, what do you think it protects against? That's right, short circuits and ground faults. Okay? The second protection, the motor overload protection, does exactly what it sounds like. It protects against overloads of the motors. And what that does is protects the motor windings, and the wire going from the disconnect to the motor. It's size smaller than the first protection. The first protection is if there is a true short circuit or a true ground fault. It's going to trip the breaker. That short circuit ground fault protection is always going to be a little bit larger on that motor, and that's going to allow for the inrush of current. The motor overload protection is going to be a little bit smaller, sometimes a lot smaller, and the reason is that is going to protect the internal parts of the motor. We don't want the motor itself burning up. Now let's learn how to size it. What size short circuit ground fault protection would you select for a 5 horsepower, 3-phase motor terminating to 60° C terminals with a nameplate FLA rating of 26 amps using an inverse time breaker? You will never size short circuit ground fault protection from the nameplate or FLA rating. I will say this one time, that if the FLC is printed on the nameplate, you can use it, but it has to say FLC, okay? FLC, it's got to say full load current. You could use it if it happened to be there. But what we're going to do is like we normally do to find our FLC, and we're going to head to our FLC tables. So let's flip to our FLC tab. Using table 430.250 because it's a 3-phase motor, what is our FLC? We start on the left-hand side for our horsepower, then we come off and T with our voltage, and we're going to select our FLC. In this case, it's 16.7 amps. Now we have to go check out a new table, okay? So everyone head to 430.52, page 308 in the 2017, and page 319 in the 2020. When we get there, the first thing that we do is we read our black bold heading. It says maximum rating or setting for motor, branch circuit, short circuit, ground fault protected devices. I feel like we're in the right place. Now on the left-hand side is going to be your type of motor, whether single phase or polyphase. Then across the top, you're going to notice different type of devices. There's a non-time delay fuse, a dual element fuse, an instantaneous trip breaker, and an inverse time breaker, which is the breakers that we normally use. So let's go ahead and answer our question. First, we find our motor in the motor column. We go down to polyphase. I want to let you know that that just means 3-phase. Now we come over and tee off with our type device. In this question, it was an inverse time breaker. Now what we do is we take that multiplier and do the math. We take our FLC, which is 16.7. We multiply it by 2.50. That is going to give us a new amperage to size our breaker by of 41.75. All right, so we took and we did our math. Now, do they make a 41.75 amp breaker? And the answer is no. I want you guys to know that with motor short circuit ground fault protection, you can use the next size up standard breaker. When we get to motor overload protection, you cannot. So with short circuit ground fault protection, you can use the next size up breaker. So we head to table 240.6a, and we check and we find a breaker that is the next size up from 41.75 amps. And in this case, it's going to be B. What size short circuit ground fault protective device would you select for a 7.5 horsepower, 115 volt AC single phase motor terminating to 75 degree C terminals with a nameplate FLA rating of 71 amps using a dual element fuse? Now, we never size short circuit ground fault protective from the nameplate or FLA rating. We're going to use the FLC. So we go and we find out what our FLC is. Now we head to table 430.248. What is our FLC? We start on the left-hand side, find our horsepower, come across to our voltage, and we're going to find that our FLC is 80 amps. Now we head to 430.52 and find our multiplier. Starting on the left-hand side and finding our motor, we come over and we tee off with our type of device. Then we're going to find that it's 175% for dual element fuses. Remember, this is just another demand factor. So we take 80 multiplied by 1.75. That's going to give us 140 amps. Now we head over to 240.6A and select the next size up. And in this case, it's going to be B. What size motor short circuit ground fault protective device would you select for a 7.5 horsepower, 208 volt, 3-phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 26 amps using a dual element fuse? We will never size short circuit ground fault protection from the nameplate or FLA rating. First thing we do is we find our FLC. Now we head to table 430.250. What is our FLC? Starting on the left with horsepower, coming over to the voltage, we find that our FLC is 24.2 amps. Now we head to table 430.250 and find our multiplier. Starting on the left for polyphase and then coming over to our type of device, we're going to find that it's 175%. We take our FLC, multiply by 1.75. That's going to give us 42.35. Now we head to table 240.6A and select the next size up. And we select B. What size short circuit ground fault protection would you select for a 5 horsepower, 115 volt AC single phase motor terminating to 75 degree plate FLA rating of 60 amps using an instantaneous trip breaker? And I love this one here. You're going to think it's hilarious. So we never size normal short circuit ground fault protection from the nameplate or FLA rating. First thing that we do is find out what our FLC is. We head to table 430.248. What is our FLC? Starting on the left-hand side with our horsepower, coming across to our voltage, we're going to find that the FLC is 56 amps. Now we head to table 430.52 and find our multiplier, starting on the left-hand side, finding single phase, then coming across to the type of device. In this case, we're going to find that our multiplier is 800%. See, we multiply it by 800, 448 amps to size our device by. Now we're going to head to table 240.6A. We're going to select the next size up, and we're going to select a 450 amp overcurrent device. Now, just for fun, we're going to take this same question and we're going to size the conductors, okay, and show you how outrageous this is. So we size the conductors like this. We would take that 56 amp FLC, multiply it by 125%. That's going to give us 70 amps. Now we head to our primary ampacity table. We size the wire. It's going to be a number 4. So legally, in this situation, you could put it on number 4 wire on a 450 amp breaker. Okay, now that would be the original breaker that you did back at the original panel. You would still have overload protection, but still, it's just outrageous to think that you could put number 4 wire on a 450 amp breaker. Now we're going to learn about motor overload protection. What size overload protection would you select for a 5 horsepower, 120 volt single phase motor terminating to 75 degree C terminals with a nameplate current rating of 54 amps? We always size normal motor overload protection from the nameplate FLA current rating, not the FLC that are listed in those tables. Let's all turn over to page 304 in the 2017 and page 315 in the 2020. All right, when we get to 430.32A, it states that for motors that are more than 1 horsepower shall be protected against overload protection by one of the following means. And it lists A1 through A4. we're only going to be dealing with part A1. It says separate overload device. A separate overload device that is responsive to motor current. This device shall be selected to trip at no more than the following settings. So here are the motors that are marked with a service factor of 1.15 or greater. And if you look all the way over to the right-hand side, it said that it has a demand factor of 125%. The next one says motors that are marked with a temperature rise of 40 degrees C or less. That's at 125%. And then all other motors, and they only require 115%. So a way to simplify it, if your motor is not marked with a service factor of 1.15 or greater, or a temperature rise of 40 degrees C or less, it's going to fall under the all motors category, and your demand factor is only 115%. So let's look at our question again. There's no service factor listed, and there's no temperature rise listed. So it will fall under all other motors. So we just multiply. We take our FLA, which was 54 amps, multiplied by 1.15. That's going to give us a new total of 62.1. Now, do they make a 62.1 amp breaker or fuse? No, they don't. So the question is, can we use the next size up? And the answer is no. With motor overloads, you are not allowed to use the next size up. So just remember, short circuit ground fault protection, everything's normal, we can use the next size up. When sizing motor overloads, however, you have to use the next size down. So we still head to our table 240.6a, and we're going to select the next size down, which in this case is going to be A. Great job. What size motor overload protection would you select for a 7.5 horsepower, 208 volt AC 3-phase motor terminating to 60 degree C terminals with a nameplate FLA rating of 22 amps? Remember, we'll always size normal overload protection from the nameplate FLA rating, not the FLCs that are listed in those tables. Also, we have to remember to use the next size down protective device for normal overload questions. So let's look at our question again. There are no service factors and no temperature rise listed. So it's going to fall under all other motors. We take our FLA, multiply it by 1.15. That gives us 25.3. Now we head over to 240.6a and select our device. And we should select the next size down, which is going to be a 25. Great job. What size overload protection would you select for a 5 horsepower, 120 volt AC single-phase motor terminating to 75 degree C terminals with a nameplate current rating of 54 amps and a marked service factor of 1.18? All right, so we're still going to go back to the same section, but we need to check what the demand factor is for a service factor. So we head over. We always size normal short circuit ground fault protection from the FLA rating, not the FLC that are listed in our tables. And we're always going to select the next size down. So let's look at our question again. There is a service factor listed. We're going to go back to our code book here, and we're going to select a 125% multiplier. We take that 54 amps multiplied by 1.25. That's going to give us 67.5. We're going to head to 240.6a using our OCPD tab, and we're going to select the next size down, which in this case is going to be D. What size motor overload protection would you select for a 3 horsepower, 230 volt AC single-phase motor terminating to 75 degree C terminals with a nameplate FLA of 15 amps and a temperature rise of 37 degrees C? Normal motor overload questions from the nameplate FLA, size down, which is going to be D. Great job. What size overload and short circuit ground fault protection would you select? 5 horsepower, 230 volt AC single phase motor, 23 amps, using fuses for the overload protection and an inverse time breaker for the short circuit ground fault protection. So first let's size our overload protection. We use our nameplate FLA rating for it. There's no service factor or temperature rise listed, so it falls under all other motors. We take our 23 amps, multiply by 1.15. That gives us 26.45. Now head to 240.6a, select the next size down. That's going to be a 25. Now let's size our short circuit ground fault protection. We're going to use our FLC. In this case, we have to look it up. In this case, we are dealing with a single phase motor, so we're going to go to 430.248. We find that our FLC is 28. Now let's head to table 430.52. We're going to select our multiplier. We take 28 multiplied by 2.50, that's going to give us 70. We head to 240.6a. We select the next size up, and it's going to give us a 25 amp overload on a 70 amp short circuit ground fault protection. Great job. Now we're going to learn the 3 different tables that we size almost all of our grounding and bonding conductors. There are 3 classifications of grounding and bonding conductors. The first one is the grounding electrode conductor. That's the GEC. That is the wire that's physically installed from, we'll say, the ground rod all the way to the panel, or the footing ground all the way to the panel. The second classification are bonding jumpers. Now, a good example of a bonding jumper is the main bonding jumper. And I don't know if you've ever seen that green screw in the back of a panel. You know how sometimes we'll screw that screw in if we're at the first point of disconnect? That screw right there is actually called a main bonding jumper. They can also be made of wire, and you may have also seen them as the strap that you turn into and connect the neutrals and grounds if you're at the first point of disconnect. Or sometimes you just use that little strap, which is made up of a piece of copper, and we're going to use that to bond the frame of the panel. That's one example of a main jumper. There's system bonding jumpers, supply side bonding jumpers. We're going to learn how to size those today. And the third classification is the equipment grounding conductor. That's the EGC. And that is going to be the conductor that we run with our circuits, isn't it? You know, it'll be either green or bare or stranded or solid. It can be any one of those variations. A good example is inside of a Romex jacket. Typically, it'll have a hot, a neutral, and a bare ground, won't it? That is an example of an equipment grounding conductor, and we're going to learn how to size those today. Let's learn about sizing grounding electrode conductors. Everyone head to table 250.66. It's on page 116 of the 2017 and on page 123 of the 2020. Pause the video now if you need to. So the first thing we get there is we check the black bold heading and make sure that we're at the right table. And I cannot stress to you enough, the next 3 tables that we're getting ready to learn almost look identical. And if you don't read the black bold heading when you get to the table, you can be off in a heartbeat. I mean, these 3 tables look almost identical. So when we get to our table, it says 250.66, grounding electrode conductor. Great, I feel like we're in the right table. So starting on the left-hand side are going to be 2 columns, and on the right-hand side are going to be 2 columns. Let's break those down now. So on the far left-hand side, those 2 columns are the size of the ungrounded hot conductors. So whatever your service is, these are based off the size of the ungrounded hots. You're going to have a copper column and an aluminum column. Okay? So if your main conductors, your hots are made of copper, you're going to select from the copper side first. And then when you come over to the other side, you're going to select depending on the make and composition of the grounding electrode conductor itself, you're going to select from copper or aluminum. Okay, so let me be very clear and very slow right here. If our mains are made of copper, we select from the copper side. If our mains are aluminum, we select from the aluminum side. Then there's a second conductor involved. It's the actual GEC itself. And we have to cross over and make sure we select from the right column, whether copper or aluminum. Because it's very easy to go copper and then want to go straight over to copper. But whatever your real world scenario or whatever your question states, you have to be very diligent to select from the respective column here and then jump over and select from the proper column here. But we're going to do a bunch of practice questions and you'll be a pro by the end of it. Now let's all flip back 1 page. Okay? Flip back 1 page to article 250.66, okay? And we're going to do a little bit of highlighting. So we flip back 1 page, and we're going to start at the beginning of 250.66, the actual article, okay? And if you read the black bold heading, it says size of alternating current grounding electrode conductors. We're going to do some very strategic highlighting here if you're allowed to do highlighting in your state. So right underneath it at part A, I want you to highlight in the black bold heading the word rod, pipe, or plate. Rod, pipe, or plate. I want you to highlight that. Then I want you to go down to the bottom of that paragraph, and I want you to only highlight 6 AWG copper. 6 AWG copper. Highlight that. And we're done here. Now let's go to part B. And I want you to highlight the word concrete encased electrode in the black bold heading of part B. Then when you're done with that, I want you to go down to the bottom of that paragraph and highlight 4 AWG copper. Then we're going to go to part C. And I want you to highlight the word ground ring. And depending on what code book you're in, for this one, we have to flip back a page or two. Okay? We have to flip over to 250.52. I want you to flip a couple pages back to 250.52. And it's in part A, and it's part 4. And you'll see the black bold heading that says ground ring. At the bottom of that paragraph, I want you to highlight the 2 AWG, because that's the minimum size it's allowed to be. And all of this is going to make sense here in just a moment, because there's 2 ways that we size grounding electrode conductors. And I think this is where most people get lost, because I know when I first got started, I didn't know the difference, and I guarantee I did it wrong every time. But there's 2 classifications of grounding electrode conductors. You're either going to size it based off of table 250.66 if the electrode is not mentioned. Or if the electrode is mentioned in your question or in your real world scenario, you're likely going to be using article 250.66, parts A, B, or C. And we're going to go through this step by step. Let's get to it. All right, now let's reiterate these ground rules for sizing grounding electrode conductors. If no electrode is mentioned, the type of electrode, so if it doesn't say ground rod or footing ground or anything like that, you're going to use table 250.66 at face value. If the electrode is mentioned, we first need to check 250.66 A, B, or C. If the electrode is not mentioned in 250.66 A, B, or C, you would go back to the table. But usually if there's an electrode mentioned, you're going to be using A, B, or C. And this is a very easy one that you can get on your test. Once you learn how to do this, you get those grounding and bonding questions, you'll be able to flow right through them. You're one step closer to being a licensed electrician. What size copper grounding electrode conductor would you select for a 100 amp service with number 4 main copper service conductors? So the first thing we're going to look at our question doesn't mention the type of electrode. No, so we're going to use table 250.66 at face value. So starting on the left-hand side, we're going to select the type and size of the service conductors. So we have to go back to our question. It says copper service conductors. So we're going to start on the copper side. Then what we're going to do is go to the right side and we're going to select the right type and size of the GEC. So when we cross over to the table, we have to look back at our question and it wants a copper grounding electrode conductor. So we go from copper to copper and we make our selection. So we come across, when we tee off, we find out that we're going to select a number 8. Great job. What size copper grounding electrode conductor would you select for a 225 amp service with 3/0 main copper service conductors? So the first thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. So starting on the left-hand side, being careful to reread our question, in this case we're going to start on the copper side. Then when we go to make our GEC selection, we're going to slide over to the right, we're going to look at our question again, and we're going to select from the copper side over here as well. And in this case, we're going to find that we would be required to have a number 4, and we would select C. Great job. What size copper grounding electrode conductor would you select for a 400 amp service with 400 kc mil main copper service conductors? First thing, does it mention our type of electrode? No, so we're going to use table 250.66 at face value. Starting on the left conductors, and in this case it's copper. Then when we cross over, we're also going to be selecting from the copper side, and we're going to select a 1/0 D. Great job. What size copper grounding electrode conductor would you select for a 400 amp service with parallel 2/0 copper main service conductors? First thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. Normally we start on the left-hand side and then make our selection, but we're dealing with parallel conductors, and this is how we handle it. So let's head to Chapter 9, Table 8. First, we need to find the approximate air drop. So we go down on the left-hand side, we're going to come over, and we're going to find the area in circular mills, just like we did for voltage drop. So each 2-aught copper service conductor, starting on the left-hand side to find our wire, then coming over 2 small columns to the circular mills and area, we're going to find that each 2-aught is 133100, and that is in circular mills. But we have 2 of those conductors, so how we handle this is we just multiply it by 2, and that's going to give us our total C mills, okay? Once we get our total C mills, we're going to head back to our original table, back to 250.66, and we're actually going to find where that conductor falls in our table. Now this is listed in C mills. If we wanted to turn it into KC mills, we would just divide by 1,000, but it's pretty easy if you just leave it in the C mills. So starting on the left-hand side, that is now the size of your service conductor. We've converted it to just one conductor. We found the area of one of the parallels, multiplied it by 2, and now we're just treating it as one large conductor. So we go down through here and we find where 266,200 C mills falls. And in our case, it's going to fall in the 3-aught, but not over 350. Because remember, this table's listed in KC mill, so that would equal 350,000 C mills. So it falls right there in the 3-aught to 350 section. So what we do is we go over, now we have to be careful again. Our question wanted copper and copper. So we make our selection, and we're going to select a number 2. What size copper grounding electrode conductor would you select for a 200 amp service with 2-aught main copper service conductors with a ground rod as the grounding electrode? First thing, does it mention our type of electrode? It does, so we may not be using table 250.66 at face value. Let's head back to 250.66, reading the black bold heading using our keywords. We've already done our highlighting, so we're going to find that part A states rods, pipes, or plates. Now looking down to our other highlighted mark, or at the bottom of the paragraph, we're going to find that it's not required to be larger than a number 6. Great job. What size copper grounding electrode conductor would you select for a 200 amp service with 2-aught main copper service conductors with a concrete encased electrode? First thing, does it mention our type of electrode? It does, so we may not be using table 250.66 at face value. The first thing we do is we head straight back to section 250.66, reading in the black bold headings, looking for keywords. Very simple. When we look at it, we're going to see that part B states concrete encased electrode. Then all we have to do is go to our second part of our highlighting, and we find out that it is not required to be any larger than a number 4. Now, this supersedes what the table says. That's why we have to be very careful, and this is where a lot of people get the answers wrong on their actual examination, because this value over here in Article 250.66 actually supersedes the table. So if the type of electrodes mentioned, go check A, B, or C and see if the answer is listed there. And we're going to select C, a number 4. What size copper grounding electrode conductor would you select for a 100 amp service with number 2 main aluminum service conductors? First thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. Starting on the left-hand side, being very careful to check the type and size of our service conductors. In this case, it's aluminum, so we have to start here in aluminum. We go down to where our conductor falls, then we have to be careful. It wants a copper GEC, which is very common. Main service HOTS, and then use a copper grounding electrode conductor. So then we come over to the right to being sure to be in the copper column, and we're going to make our proper selection. And we select A. What size copper grounding electrode conductor would you select for a 225 amp service with 250 kc mil main aluminum service conductors? First thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. Starting on the left-hand side with the type and size of service conductors, very careful, it's aluminum. Then when we make our crossover, being sure to go to the copper side because that's what it's requesting, We make our selection, and we're going to find that it's not required to be larger than a number 4. What size copper grounding electrode conductor would you select for a 400 amp service with 500 kc mil main aluminum service conductors? First thing, does it mention the type of electrode? No, so we're going to use table 250.66 at face value. Starting on the left-hand side with our type and size of service conductors, in this case aluminum. Then when we cross over, it's asking for a copper grounding electrode conductor. When we look through there and we tee off, we're going to find that it's not required to be larger than a number 2. Now let's learn how to size equipment grounding conductors, EGCs. And for that, we're going to use table 250.122. It's on page 125 of the 2017 and on page 133 of the 2020. And I love this table because it's so easy to use. There's not all these crazy exceptions. It's very simple. So when we get there, the first thing that we do is we read the black bold heading to make sure we're in the right table. Minimum size equipment grounding conductors. Great, I feel like we're in the right table. Now this table's laid out like this. It has the size of the overcurrent protective device on the left, then the size of the EGC on the right. So we have our overcurrent protective device in amps, and then we have a copper and aluminum. So we just have to be careful when we cross over to make sure we select, from the proper column, but it's really simple. Size of the breaker or fuse on the left, copper or aluminum on the right. Let's get to it. What size copper equipment grounding conductor, EGC, would you select for a service with a 200 amp main breaker and 4-aught copper conductors? Doesn't matter what the conductors are. In this case, it's always based off the size of the overcurrent protective device. So we head to table 250.122 using our EGC tab. We always size our EGC based off the overcurrent protective device size. So in this case, what should we use for a copper at 200 amps? When we slide over, being sure to select from the copper side, we're going to select A. Great job. What size aluminum equipment grounding conductor would you select for a service with a 100 amp main breaker with number 2 aluminum conductors? So we head to table 250.122 using our EGC tab. Then we're going to base our EGC off the size of the overcurrent protective device. And we're going to be sure to cross over to the aluminum side, and we're going to select D. Great job. Now we're going to learn about sizing bonding jumpers. This is done in table 250.102C1. Now there's not a tab for this one, but if you watch my how to make your own tabs video that is back in week 1, it will show you how to make your own tabs. And this is one of the ones that I highly recommend making. I call it bonding jumpers or something like that. But to head to this table, we're going to head to page 119 of the 2017 and page 127 of the 2020. When we get there, we check the black bold heading to make sure we're in the right table. And when we look at it, it says grounded conductor, main bonding jumper, system bonding jumper for alternating current. Great, I feel like we're in the right table. Now this table is laid out very similarly to the GEC table, the 250.66. That's why you always read your black bold heading to make sure you're in the right table. So we're going to have the size of the undergrounded hots on the left, size of the bonding jumper on the right. We have copper and aluminum, and we have copper and aluminum. So these questions are laid out very similar, but we have to make sure that we're in the right table. What size copper main bonding jumper would you select for a 200 amp service with 2-aught copper conductors? So we're going to head to table 250.102C1. You're going to size the main bonding jumper based off the largest ungrounded service conductor. Starting on the left-hand side, we select our type and size of the service conductors. In this case, it's copper. Then on the right side, we're going to go over and we're going to select a copper main bonding jumper. And we're going to select A. Great job. What size copper main bonding jumper would you select for a 100 amp service with 1-aught aluminum conductors? So we're going to head to table 250.